All right, it's time for logarithms. So here is an example of an indeterminate form of type 0 to the power 0. Okay, we're dealing with our good friend x to the power x. This limit, the limit as x approaches 0 from the right of the function x to the power x, this is actually a limit that we have looked at before. This function looks sort of like this, and then it goes off that way. And right here, it approaches 1, right there, at 0. It comes and approaches 1. Although actually it's undefined, so I drew that as a closed dot, but it should be an open dot. It's got this undefined point right there, but it is approaching 1. So the answer here is going to be 1. And we know that from a long time ago when we looked at this numerically and figured out just by like looking at the graph and looking at the output to the function as x approaches 0, that this seems to be approaching 1. But a numerical approach like that is not rigorous. It doesn't prove anything. So now that we know L'Hopital's rule, and now that we've done that logarithmic differentiation, we're going to apply some similar rules using log properties to show that this limit equals 1. And we're going to prove it. Okay. So let's do a proof. Okay, first thing we're going to do is we're going to do some shenanigans with logarithms. So let's write y equals x to the power x. That's our function we're working with, right? Just like when we were trying to take the derivative of this function, we're going to do the log of both sides. We're not actually trying to take the derivative of this function. We're just trying to simplify things. Let's take this x and pull it down. X, natural log of x. Now, if I convert this back to exponential form, y will equal e to the power x times the natural log of x. So that means that this limit is the same as the limit as x approaches 0 of e to the power x times the natural log of x. Like that. So now the question is, well, what is the limit of that inner function? X approaches 0 from the right of x times the natural log of x. The question is, what is that limit equal to? Well, that's very similar to, actually, no, wait, I skipped that example. So we haven't actually done anything that looks anything like that before, but if we analyze the situation, x is approaching 0, certainly, right? And as x gets close to 0 from the right, the natural log of x is approaching negative infinity. Okay? So 0 times negative infinity, that is an indeterminate form, right? 0 times infinity. It doesn't matter that it's negative infinity, it still counts. So what we want to do is do one of those reciprocating tricks, either one or the other. So we can either write this as natural log of x over x to the negative 1, or we can write this as x over the natural log of x to the power negative 1, like that. So reciprocate the natural log. Now, I don't know about you, but differentiating the reciprocal of the natural log sounds kind of annoying. But differentiating the natural log sounds easy. Now, word of caution, back when we did this with x times e to the x, when we put x to the negative 1 in the denominator, when we differentiated that, the power went down to -2, and then -3, and -4, and we got stuck in that infinite loop. And that didn't work. But this time, spoiler alert, that one is going to work, whereas this one is not. Try it. Doesn't work very well. But this one is going to work great because that is in the format negative infinity over infinity. So infinity over infinity form. So we can apply L'Hopital's rule to that there and get a limit as x approaches 0 from the right of the derivative of natural log of x, which is 1 over x. And then, yes, differentiate x to the negative 1 and you get negative x to the negative 2. I know that power went down and it kind of got more complicated, but actually the fact that we got 1 over x in the numerator is going to make this so much simpler. This is terrible. Let's fix this. Let's fix this. This is meant to be. Oh, this is just abysmal. Let's move things around. There's a negative first of all, so let's put a negative in there. There's one of these negatives. X to the negative 2. Move that up to the numerator. That's x squared. This 1 over x, that x will end up in the denominator like that. And then one of these x's cancels with one of these. So this whole thing is just the limit as x approaches 0 from the right of negative x. Just that. Well, that equals 0. Okay, so what we were dealing with there was the limit of x times natural log of x. That's this part, right? So if that's u, this is our u, then what we found here is that u is approaching 0. Okay, so now we can say that this is equal to the limit as u approaches 0 of e to the u, which, direct substitution, e to the power 0 is 1, which is what we were trying to prove. So that is an example of how you can solve a limit by first doing some logarithms, right? Just doing a little bit of logarithm business to convert your function into something doable. And then you get this, which is a product of two functions, and that is in a 0 times infinity form, which you then manipulate into either infinity over infinity or 0 over 0, depending on the situation. Apply L'Hopital's rule to that to figure out what that limit is, and then you can go back and do a u substitution to get that limit of the exponential function you were working with, and that'll work. Again, sometimes the road is long. Many steps are required.